record. Let me start the record. Okay. Okay. So what are you trying to show? So look at the joint distribution created by the protocol on Z, Y, and E. Okay. So here Z is supposed to be the true secret key, and Y is the seed, and E is the environment. Okay. And we want to say that this is very close to uniform on Z. Okay. Times the marginal on Y and E. Right. So okay. So is this case? So we want to show that this is very small. So we'll just write down what this quantity is. Okay. So let me write PYE and then right. So so the margin on Y is the same in the first term as well as the second term. So I'm just pulled it out, and now the different coordinate wise is only coming from Z. Okay, so I take the conditional probability on Z given YE, and for the second term, of course, I mean UZ is in product with PYE, so there's just 2 to the power minus n. Take absolute values here. Okay. Yeah, so this is the precise description of the L1 distance. And now let us see what this is. So remember, Y was the seed random variable. So Y is independent of everybody else. Okay. So it is 2 to the power minus d for Y, and then sum over YE. So basically, the what I'm using out here is just this PYE is 2 to the power minus d, okay, times P, right? So that's what I'm doing. Okay. Okay, this is the next crucial step. Is this clear, Hari, Aditya? Yeah. So PYE, I know is 2 to the power minus d because Y is independent of everything else. Okay. And remember, Y was chosen after the random variable E was created. So recall the setup was that, let me remind you, the setup was that there was Alice and Bob, and then they shared X, okay? Right? So they shared X, but X was not completely secret from the environment. So there is the environment out here. So let me say there is this other box sitting in the middle, which is the environment. So this is A, this is B, this is E, and the environment has this. Okay. Okay. The contents of the environment are captured by the symbol E. Okay, from some alphabet, and we started off by saying that X was partially secret from E, right? So the entropy of X given E was larger than some K. And again, to recall, like X is quite large, it's n bits long, okay? And of course, so let us say, okay, so we said that the secrecy guarantee, I mean, our first guess was just the conditional Shannon entropy, but it turned out that's not the right one. So the correct one was H min epsilon, but we'll run this proof with H min, and then the proof for H min epsilon is just a simple observation after that. Okay, it's an epsilon perturbation of this. So and usually the scenario is K is much smaller than N. Okay, and then if you recall now, right? So X and E have been correlated in some way, but there is still a partial secrecy of X given E. Okay, so this condition is there. And now Alice and Bob want to extract the secrecy out into some M bits. Okay, so for that they exchange the seed random variable Y. So Y is a small number of purely uniformly random bits independent of everything else. So Y is like in 0, 1 to the D. Okay, and what Alice does is right. So so this is what I'm calling Z. Yeah. Okay. And now the hope is Z will be completely independent of E. I mean, or almost completely independent of E and perfectly uniform. So, and what is Z? Z is something like 0, 1 to the M. Okay. And I mean, we expect that M is less than or equal to K. Okay, because K was the amount of secrecy that X had relative to E, right? So, and I just want to extract the secret bits out. Okay, I may not be able to extract all the K, but I want to extract M, which is close to K. And I want D to be much, much smaller than, yeah. So let us say the D is smaller than, much, much smaller than N to start off with. Okay. So ideally, I want D to be very, very small, even smaller than N. But anyway, the yeah, and what was the criterion for correctness of the protocol? Just a second. So this is approximately N. Okay. Yeah. Right. So under this setting, you can see that the probability distribution on Y and E is a product probability distribution, right? Because E is only correlated to X. So that's the split out here. And then I'm writing what is the probability of Z given Y. Okay. So I have to sum over all the x's such that fxy is equal to z. The extractor function output z. Okay. And then, of course, these x's will now be distributed according to the random variable capital X conditioned on. Okay. Yeah. So is this clear? Okay, so now we'll upper bound the L1 norm by the L2 norm using Cauchy-Schwarz inequality. Okay. So actually, let's do it this way. Okay, so last time I was doing the Cauchy-Schwarz differently, but let me try something else. But then I've forgotten the sum over Z. Okay, so I believe we can do this by a simpler Cauchy-Schwarz inequality. So essentially, I mean, we will just we are just going to apply Cauchy-Schwarz on this part. Okay, on the highlighted part. And we'll treat this as a dot product between one vector, I mean, whose entry you can see between the absolute value sign, and the other vector is the all ones vector. So just to put everything short, this is less than. What do I do? Okay. There's also sum over y. Yeah. Okay. Sorry. So that's no. So let's do the Cauchy-Schwarz a little more carefully. So sum over E B sum over YZ. Yeah, we'll do the Cauchy-Schwarz like this. So one times yeah. So this is still equal to. There's the same summation but written in a different way. So anyway, y will become clear very soon. So this is right for applying Cauchy-Schwarz. I'm just telling you what is the Cauchy-Schwarz. What are the two vectors? This is all ones vector, and this is the other vector whose entry is given by the quantity between the absolute value signs. Okay, is the rewriting clear? Yeah. So now we are going to apply Cauchy-Schwarz. So the first Cauchy-Schwarz, so I'll look at the L2 norm of the all ones vector. So that is very easy. That is basically, I mean, the cardinality of the set capital Y and the set capital Z. So which is D plus M by 2. Okay. And square root sum Z. Okay. And now okay, that's it. So is this step clear to everybody? So this is the Cauchy-Schwarz. Okay, so now let's start simplifying this. Okay, so let me just write down one step, but this is the easy one. So this is 2 to the power m minus d. Just a little bit of simplification. That's all. Okay. So now, as you can see, okay, we have cleaned things up a little, and we have to analyze basically this term. The term, so should also say, okay, so I mean, there was some reordering here. I moved in the sum over y inside, as I said. Okay, so the yellow part is basically where the I mean, all this Cauchy-Schwarz trick was done. Okay, so now let us evaluate the term inside the square root sign. Okay. So sum yz. So now there will be so this square minus 2, whatever, 2 to the power minus n plus 1. Okay, then again this plus 2 to the power minus 2n. Okay, so I'm just opening up this summation. Okay, in the Cauchy-Schwarz. So now, what is this equal to? Yeah. So this is yz. So here the most crucial term is the first term. So anyway, let's write down all the terms and put it up. So the first term I can now write like this: sum over x prime, okay, x prime, such that f xy equal to f x prime y equal to z. Okay. This is the first term. Now the second term, okay. Okay. So this is so okay. So actually, and yeah, so this is constant term. So let's just pull it out and evaluate it. So this is plus 2 to the minus 2n, okay? And then the sum over y and z. Okay, so this is 2 to the m plus t. Yeah. And now, so let's just pull out the first term. Okay. And now, okay, so let's look at the second term. So the term in this bracket, sum over all x's such that fxy equal to z, probability of x given e. So this will add up to what we already know. It is just the probability of z given e, which we started off out here, right? So yeah.
So this sum over yz is only over the first and second term, right? In the second last expression which is written.
Yes, yes.
Okay.
So yeah. So okay, and then so maybe let me even write it out here instead of repeating this. So this is the probability of z given e. Okay, and now when I do sum over yz, probability of z given e. So sum over z, probability of z given e will be 1. Okay, and then just the sum over y comes out. So this is something like 2 to the power minus n plus 1, and this is 2 to the b, and plus 2 to the power minus m, okay, plus t. So a little bit of simplification before we go on to the main term. So the main term was the first term. Okay, and this is basically minus 2 to the power plus b plus 1, right? Sorry, this is n plus 2. Okay, yeah. So the I mean this quantity is twice the second quantity is twice the third quantity. That's all. So I get this 2 to the power minus m plus t. So far so good. Now let us go to the first quantity out here. Okay. So let me write it down. This is where all the fun lies. Okay, sum over yz, and then the sum over xx. Now, remember we are using two universal functions as our extractor function, right? So let me write it out here. Okay, so what do I know? I know that probability of z is 2 to the power minus 2n. Okay, for any x not equal to x prime, z prime, right? So recall we had this family of functions, okay, from n bits to m bits, and this family is indexed by y, where y is d bits, and our extractor f of x comma y was just the following. Go to the yth function in the family. That's why I've written f subscript y. So take the yth function and apply x to it as the input, and the output is what we want, z. Okay. So we have this out here. So let us make use of this fact while simplifying this. Okay. So we will split this summation into two parts. Okay. So remember we have the sum over x prime. So x prime are completely independent of each other. So we'll split the summation into two parts, x equal to x prime and x not equal to x prime. So first let me write x equal to x prime. Okay. So sum over x f xy equal to z. Okay. And this will be p of x given e square. Okay. And plus yz. So now this is the sum over x not equal to x prime. Okay. Let me write it down there. And then of course f x x y equal to f x prime y equal to z. Okay. Probability of x given e, probability of x prime. So okay. So now let's see. Okay. Okay. So let's look at the first term. Okay. So the first term, see that I have a summation over x's such that fxy goes to z. Okay. And then yeah. Okay. And then I have a summation over z also. Okay. So overall, this means that I'm summing over all x's, right? So I bunch the x's into groups. In each group, the x's map to the same z. Okay. And then I'm just taking the sum squares of those probabilities. But then as I sum over all groups labeled by the different z's, in effect, I've summed over all x's. So this thing is actually sum over y, sum over x, separated, all the x's, probability of x given e square. And the second one, yeah. Okay. The second one is what we would like to call the collision probability, okay, which Shantan was alluding to last time. So what I'm going to sum, so I'm going to sum over y and then sum over x not equal to x prime, fx with the condition that f of x comma y maps to z and f of x prime comma y maps to z. So this is nothing but 2 to the okay 2 to the power d times some whatever this, okay, x not equal to x prime. Okay. And now so this is the probability. So remember the probability is over the choice of y. So I should say probability that f subscript y x equal to f subscript y prime. Sorry, same one. So f subscript y x prime. Okay, equal to z. Okay, and then there is probability of x given e, probability of x prime given e. So let me move this down. So this is a very important step. Okay. So let's go back again. The first one was easier. So in the inner summation, I'm summing over all x's that map to z, and then I'm summing over all z's out here. So overall, I'm summing over all x's. Okay, so that's the explanation of the first thing. For the second thing, okay, I split the summation of yz into first sum over z, then sum over y. Okay, what do I mean by summing over y? So remember, the probability of y is of the probability of getting a single particular symbol y is 2 to the power minus d. Okay, so think of it. I'm just multiplying this by 2 to the power d, and then putting in a py out here. Okay. Now summation over x not equal to x prime. So what are the so fix a x not equal to x prime. What are the y's that send x to z and x prime to z? Okay, that is precisely this expression. That probability under the uniform choice of y, that f subscript yx equal to f subscript y x prime equal to z. Okay. So summing over I mean x not equal to x prime with this constraint just means a sum over x not equal to x prime. Okay, and then multiply by this factor of probability. Is this step clear? Yeah. Is this step clear to everybody? Yeah. Okay, so let's go ahead. So this is very crucial. Okay. So now let us see what this quantity is. I claim that the first quantity is nothing but H2. Okay, the relative entropy of x given E times yeah, there's also the sum over y, so that will give me 2 to the power p. And the second term, there's this 2 to the power p that comes out. Then, okay, by the property of the two universal hash family, the probability that this is going to happen. Okay, remember x is not equal to x prime, so this is 2 to the minus 2n. Okay, so this is sum over z, sum over okay. So px given e, px prime given e, and this is 2 to the power minus 2n. Okay. Okay, so this is okay. So this is h2 of x given e. So we will see why this is 2 to the power d. Actually, let me put a less than, okay, and there is 2 to the power d. So so I can I can sum this over z. I mean nothing here depends on z. So this will give a factor of 2 to the m, and remember there's 2 to the minus 2m. So this becomes 2 to the minus n. Okay, and this is some x not equal to x prime, but I'm going to like throw up my hands and sum over every pair. So sum over x prime. Okay, p x given e, p x prime given e. Okay, so what is this? This is 2 to the power d h2 x given e. Okay. And so this is 2 to the power minus m plus d. Okay, so this quantity is nothing but summation over all x probability of x given e whole square. Okay, which we know is 1. Okay, so, okay. So whatever I got, this was the first term. So let's come back out here. Right. So this 2 to the power minus m plus d cancels with this term out here. Okay. So remember we're evaluating the first term. So I get this cancels. So the first term evaluates to just 2 to the power d times h2. So what? So remember what was this? This was the quantity inside the square root out here. Okay. So what have I proved? So let me come back. That this quantity, okay, is less than 2 to the power d, and oh sorry, this is not h2, it is 2 to the power h2. So 2 to the power, actually this is 2 to the power twice h2, we will see right in a moment. Okay, so it's not h2 but 2 to the power twice h2. So the conditional relative entropy. So this is 2 to the power twice h2. So what have I shown? I've shown that this is less than 2 to the power d plus twice h2 of x given. Okay. So this was the quantity inside the square root. Okay. The quantity inside the square root. And then it gets multiplied by whatever is outside. Okay. So, and this was an upper bound on the L1 distance. So what have I proved by putting all this together? So the L1 distance, probability of ZYE minus L1 uniform on Z times YE. Okay. So this is less than m minus to the power m minus d2. Okay. And remember there was a sum over EPE out here, but that does not affect anything because this will just add up to 1. Okay. So this is 1. Okay. and now this is 2 to the power. So there was a square root of this. So square root 2 to the power d plus 2 h2. Okay. So this is 2 to the power n, and there's a 2 to the power minus d by 2, which cancels with 2 to the power plus d by 2. So what this comes out to is sorry. So this is there's also minus sign which I forget. Sorry. Yeah. So this makes it m minus h2. Okay. So this is the final upper bound. We have shown that the L1 distance between the output of the protocol and the ideal thing, which is uniform on the output times marginal on the contents of the environment, including the seed. Okay. So that is upper bounded by something which looks like this. So what does this say? This says that I can make my output length m pretty close to H2, okay, the conditional relative entropy of X given E. Okay, so I mean, I only have to prove this quantity, which I'll do finally. So what does this tells us? So this tells us that take m equal to X given E minus something like log 1 by epsilon. So I can make the output length very close to the conditional relative entropy. Remember, this is the amount of privacy X has, the raw secret key has from the environment. And I have almost extracted that entire amount, okay, except for this additive factor, log 1 by epsilon. Okay. So if I do this, then this will be less than epsilon, which is what I wanted. I mean. So is the okay, and remember we were talking of h min out here, so I'll just use the fact that okay, remind you that h2 okay, is greater than h min. Okay, so if I can extract the conditional relative entropy number of bits, then of course I can extract the conditional Rayleigh mean entropy number of bits. Okay, and you also know that H2 and H min are approximately close. We have even seen that. Okay. So yes, surely, I mean, you can come up with a more accurate statement using H2 that, okay, well, you know, why H min? You can extract up to H2 the number of bits. But anyway, we know that H2 and H min are not that different. I mean, H min is convenient for other, I mean, more advanced work on extractors. Okay. Okay, so, but what we have seen today is that you can extract the conditional relative entropy of X given E, or the conditional Rayleigh mean entropy of X given E. So you can extract almost the amount of privacy which is there. Now, what is the seed length? The seed length is pretty large out here. The seed length D is okay. So it's actually 2n out here. I mean, I wanted seed length much smaller than n. Okay, but if I take the two universal extractor hash family, which I told you last time, that will be 2n. So there has been subsequent work which has really brought this D down, and that subsequent work works better with HMIN. So that's why I'm keeping to HMIN. But anyway, I mean, one can still make a case for the hash family extractor, because whatever this D is, remember we are not counting D in the final extraction, right? We are saying that the extracted true secret key Z is independent of Y and D. Okay, so Y is 2n bits long. That doesn't matter. I mean, it is still independent of that. Okay. So that's the amazing thing. And the only thing left is to finally prove this one. Okay, that sum over x px square is equal to this Reni 2 and Fleury, which I mean essentially follows from the definitions. I'll do it shortly. Okay, any questions about this proof? Any doubts? Yeah. Sorry.
This seed length of 2n, this comes up because of the universal
Hash
family.
family. Yeah, you can bring it down. You can bring it down to 2m, where m is the output length. A little bit more work. But I mean, the dream that I was trying to sell you is that D is much smaller than M. Okay, so let me tell you what one knows. Okay, so the state of the art. So okay, so this is, let me even tell you, not state of the art, but this is the easiest one to prove, and I mean shows you the power of the hash. I mean hash family. So the state of the art, which is I mean the proofs are much more complicated and they go far beyond all these hashing things. So state of the art is, write it here. I mean, you should not think that this is the best that is known, but this was the earliest extractor, which showed that. I mean, the amazing thing here is that I know that there is some privacy in the raw secret key from the contents of the environment. But how that privacy, I have no idea, other than this bound on this entropy, which is K. Okay. The amazing thing is that whatever be the distribution, as long as you guarantee me that the amount of privacy is is greater than equal to K, you can exactly extract that much amount of privacy out. Okay. So this will work for every distribution satisfying this privacy guarantee. Okay. So this is kind of like, that's why the name extraction is there. So, I mean, if you look at X given E, yes, there is that much privacy, but you do not know which bit is private. Okay. In fact, a single bit may not be private. It's some combination of bits which is private. Doesn't matter. This extractor will extract all the privacy out, all the juice out, and it will extract and distill it into some M bits. Okay. And the M will be completely independent of everything else and be very close to it, which is what we show. So the state of the art here is
And do we know how close is M to K? Like what is the relation between M and K? Can that be stated?
no. So H2 of X given E is K. Okay, that was my
Okay,
definition.
okay. Yeah, I see. Okay.
So I can go to K minus log 1 by epsilon.
Yeah. Okay. I see. Yes.
Okay, so the state of the art says we can achieve M very close, similar to M approximately K with D equal to something like order log n by epsilon. Okay, something like this. So this is the state of the art. And remember, I mean, we want the extractor function to be efficiently computable. So yes, the universal hash family is efficiently computable. But before people could get this, there were existential questions like, are there extractor functions which achieve these parameters? So the answer is yes. So people proved it by a combinatorial like counting argument, but that does not give efficient functions. But the state of the art is there are efficient functions which achieve B like this. Okay? But these are, I mean, a topic for a different course. Okay, so indeed, I mean, you can extract almost all the privacy out, and the seed length can be made very small, much smaller than N, K, and K. Okay. Okay. So any further questions? Then I'll just proceed to prove this business about H2. Okay. So let's try to prove this claim. So the actual claim will be this. Remember, there was this summation over PE hanging out of this whole business. Where was this? There's a sum over the P out here, right? So to really formally prove it, like you have to move the P into the square root by concavity of square root, the Jensen inequality. So you can move that in. I mean, exactly achieve this. I didn't want to, I mean, overload the thing. So the formal claim is that sum over E, PE, then sum over X square is equal to 2 to the power minus H2 X. Okay. So this is actually, I mean, following from the definition of the proof. So remember what was H2? X given me. So this is, so it was like, okay, so there will be a minus half coming out. Remember, like H alpha had a factor of 1 by alpha minus 1. Okay, so here alpha equal to 2. The okay, yeah, I mean the Rayleigh divergence. So there's a minus half out here, and then there is log. Okay, so let me remind this. So this is d2 of xe times x, the marginal of sorry h2, right? So this will be the all ones vector on x times so let me so I have a probability distribution on x and e. Okay, so the conditional relative entropy of x given e comes from the relative divergence. So this is take the joint distribution on x and e. Okay, and take the divergence between the joint distribution and this one. Okay, so put the all ones vector on the on x, okay, on the first system, and the marginal on the second system. So I hope you recall this from an earlier lecture. So what is this? So this is what is the formula for d2? So there will be a minus half log. Okay, so probability of xe, then flat xe, and this is all ones vector on x times e. So that, I mean, that will just evaluate to p. Okay, so this is the expression for the divergence, and there is a summation, of course. Sum over x. So just recalling the definitions. So this is equal to, okay. So minus half, then log. Okay. So sum over e, then okay. So this is sorry. So there is alpha divergence. Sorry, it's not this ratio. So this is square, and this is yeah. So let me write it down. Okay. Sorry, this is the Rayleigh 2 divergence d2, right? So the so the first term has to be raised to the power alpha equal to 2. The second term has to be raised to the power 1 minus alpha, which is -1. That's why it comes in the denominator. Okay, so we get this fraction pxc squared and px. So what does this come to? So this is I was totally confused. So there is also no pxc. Okay, so that's all. So this becomes, okay. So the joint probability just of x with e, I can write it as yeah. So actually, so this joint probability I can write it as p times p of x given e. So p square cancels with p out here. So just one p remains, and then this becomes px given e square. So this is exactly what I have in the claim. So there's a factor of 2 out here. Yeah, so this 2 is coming from this half, and then this proves that. So is this clear? So just write H2 in terms of D2 out here. Recall the formula for D2. Yeah, so in the formula for D2, I mean, it is the log of the sum. Okay, so okay, for the first probability distribution, raise it to the power alpha, which is 2. Second probability distribution, you raise it to the power 1 minus alpha, which is -1. So it just turns out in this form, and that's just the definition of relative divergence. Is this clear, everybody? So that's it. So yeah, so I had also said when we were doing the Rayleigh divergences that Rayleigh 2 divergence is also an important quantity because it's connected to the collision probability. So you can see in this analysis, right? So this is where I mean when I studied when I studied this term, like x not equal to x prime, I was looking at the collision. That what is the probability that for x not equal to x prime, the application of the function gives a collision. That means gives the same value as the output of the function. So in these kinds of collision probability analysis, the D2 quantity appears naturally, and collision probability occurs naturally because often we use Cauchy-Schwarz to bound L1 distances. So if you try to bound L1 distances by Cauchy-Schwarz, you have to square things. The moment you square things, this collision looking terms will come in. And then if collision looking terms comes in, then D2 or H2 will come. Okay. So that's why the Rayleigh 2 divergence is also important. Yeah, any further questions? Hari, is it okay?
Yes.
Okay, good. So let's start a new topic first. Yes, of course. I mean, this will be the last part of the classical part of the course, which is the first half. But yeah, so it's an introduction to what lies ahead. So far, what we have been doing is like one-shot information theory, but we have been looking at point-to-point channels. Like there's one sender, one receiver. Okay, so we did message compression, one sender, one receiver. We did noisy channel coding, one sender, one receiver. We did like noiseless source coding, source compression. So there's basically only one sender. Okay. So now we'll move on to multi-terminal information theory, where there can be several senders and or several receivers. Okay, but yeah, but before we do that, yeah, so it is still single sender, single receiver, but you will see that, I mean, there is also kind of a second receiver slipping. So the first simplest multi-terminal channel that we will study is what is called the wiretap channel. Okay. So what is the wiretap channel? So there is the channel. Now, so let me explain what I mean. so there is this legitimate sender Alice, the legitimate receiver Bob, but there is this eavesdropper on the environment. Okay, so we saw the environment for our key distribution thing. So it's like the same thing, the environment of the eavesdropper. So there is the eavesdropper here, which can get some information about what Alice is transmitting. So the setup is that there is this message coming in from the outside. Okay, so the message can be any number from 1 to 2 to the r. So we are looking at rate r. Okay, remember the single shot. So message set is of size 2 to the r. So Alice gets his message set. So then she first encodes it. So there is the message M, which now Alice encodes. Okay. So what can she encode into? Remember, this is a channel. So this is the channel. So the channel has an input alphabet X and an output alphabet Y. Okay. So Alice will encode her message M into a probability distribution over the input alphabet of the channel. So it's P of X given M, just as in noisy source coding. Now what the channel does, the channel gets a symbol X coming from this conditional probability distribution. It will output a symbol Y according to the probability distribution P of Y given X. Okay, but yeah, but I would like to, hold your horses. So we are talking wiretap channel. So there is this eavesdropper which is also getting some information about X. Okay, so how do I capture this? So let's say there is this. So really, the joint okay. So there's a joint distribution on the legitimate channel output and and what the eavesdropper gets. So this is modeled as probability of YE given X. Okay. So this is the characteristic of the channel. Okay. So yeah, so Eve has some knowledge about X coming from E, and remember the E can be correlated to Y. So Eve has some idea of what Bob is going to see. Now Bob will pass the output Y through a decoder. So pass the output Y through a decoder, and that will be his guess for what M was sent. So we are going to say that. Okay, so his guess I'm calling it M hat. So probability of M hat given Y. So this is like the noisy channel coding, except that there's the eavesdropper E. Okay, so I have P of Y given X instead of just P of Y given X. And the question is, what is the maximum achievable rate that Alice can get? So how large R can be? Okay. So the message M has to go from Alice to Bob. Bob should be able to recover M. Okay, let us look at, the simplest sounding definition. Every M should be recovered high probability. In other words, like probability averaged over the encoding operation. Okay, then the decoding is also a private decoder. The decoding operation and the randomness of the channel, probability that M equal to M hat should be larger than 1 minus epsilon for all M, and for all M, what Eve sees should be almost independent of it. Okay, so let me do the requirement. Okay. So for all M, okay, probability. So this probability is over the okay. So I fixed an M. So this probability is over the encoding channel and decoding. So probability M not equal to hat M is less than epsilon. So this is the correctness. And then there is a secrecy requirement. It says that, okay, probability of E given M, I put in a fixed M. So what E gets is a random variable. So this probability distribution of E given M should be approximately close to a fixed probability distribution. So I mean, let us say the marginal distribution on E. So this is the sequence. So are the formal requirements clear? So for all n, there's a correctness requirement. Probability that the decoded output hat m is not equal to m is less than epsilon. Then there's a secrecy requirement which says that the probability distribution on E should be almost independent of m. So this is what I'm saying. Like E given m is approximately equal to the marginal distribution. Are the definitions clear, Hari?
Yeah.
Yeah. Okay, so now let's see what we can do. So what is the strategy? So we go back to the noisy channel coding strategy, and we'll modify it slightly to fit for the wiretap. So what was the noisy channel coding strategy? I had to construct a code book, and there the prescription was construct a random code book. So what was the random code book? So take x1, x2, okay. So on. So let me write what I mean. Okay. So I'll explain what I mean in a moment. So in the noisy channel coding, how did you construct a code book? We said that, okay, so let us say, of course, like fix an input problem. So fix the probability distribution on the input alphabet, px. Okay. Then, okay. And then the prescription was choose IID samples, okay, x1, x2, but it went up to x2 to the r. So 2 to the r IID samples from the marginal px, okay. So, but here I'm saying choose some more samples, okay. Choose IID samples from px, okay. Now, if I wanted a capital R, I will not choose 2 to the r samples, but I'll choose something more. I'll choose 2 to the capital R plus small r samples. What is small r? We'll fix shortly. So, I've just labeled the samples like x1, x2, like this x2 to the little r, x2 to the little r plus 1, x to the 2 to the twice little r, so on after this. So pick these many IID samples. Now group them into blocks of size 2 to the r. So this is the first block. This is the second block, so on, and somewhere here is the last block. Okay. So the number of blocks is 2 to the capital R. Okay. So this is group into 2 to the capital R blocks. Each block of size 2 to the little r. Okay. So group. Now to send the mth message, what Alice will do. So okay, so this is the code book. Once the code book has been chosen, it's fixed for all time and revealed to all parties. Even Eve knows the code book. and Alice and Bob know this code. Now to transmit a message M, transmit M, Alice chooses a random sorry, M plus K. Okay, so what am I saying? So let us say Alice wants to send the second message, M equal to 2. So she'll choose a random code word from the second block. So to transmit M, Alice chooses a random code word from the mth block. Okay, so this is nothing but that is random code word from mth block. Okay, I'm just writing this. So a random code word from the mth block will have index m plus k, where k is randomly chosen from 1 to 2 to the little r. Okay. Mth block. So I think this has to be yeah. So m minus 1 probably. Yeah, you can figure it out. Yeah. Okay. Yeah. So the idea is choose a random code word from the mth block and transmit it to the chat. Is this clear? Sorry? Yeah. Yeah. So now what Bob will do, Bob will try to recover what the code word has been sent. So Bob recovers the actual code word. So I mean, Bob is really only interested in the block number. Okay. I mean, Bob wants to know finally what the message is, but Bob even does something more. He recovers the actual code word. Okay. So he even knows which code word within the block was sent. Okay. And what Eve sees, okay. So remember, the Alice chooses a random k within the mth block. Okay, and this is chosen using private randomness. So Eve has no idea. Uh, Eve has no idea which code word in this block was sent. So what Eve sees, okay. So probability of E given X. Okay. So what Eve sees is okay. Sorry, 2 raised to minus. Okay. So what Eve sees is an output for a random code word within this block. So suppose I'm talking the second block. Eve sees the effect on her random variable E for a random code word in the second block. So what is the random code word in the mth block? That is given by 2 to the power m minus 1 plus k. Okay, the code word X for that. Okay, so this X influences E. So the probability distribution is P of E given X, okay, on this random code word. And as I said, because this code word number within the block is chosen by private randomness, the effect on E is randomized. So this is the average within that block. Okay, so this is the average over the mth block of the effect on E by a random code word within the block. And okay, so this is the situation on E, and we hope that this quantity is close to the marginal on E. And hope is this is close to P. Okay, is this clear? Hari? Yeah. Yeah. Okay. So for Bob to recover the actual code word, so remember so the number of code words that go in, like in full glory, are 2 to the r plus r. So all I record, so we need that r plus r is less than I epsilon min, okay, of x with y under the distribution p. Okay, so what is the distribution p? So there is, I mean, you choose a distribution for the input variable x, then the channel characteristics will set y and e according to x. So this is the underlying distribution. Okay, so we need this, and so this will guarantee correctness for Bob. So let us say Bob's correctness, and we want secrecy from E. So for that, we'll use the covering lemma. So this is the packing lemma, and the covering lemma says that as long as I is larger than I epsilon max of x e given p, okay. So this sample average, okay, this average over the mth code mth block is close to the marginal distribution. Okay, so this holds in expectation over the choice of this code words from the marginal px. Okay, so this holds in expectation, and then you can, I mean, set random variables and make it hold do some expectation. So this is Eve's secret. So this is what we require. So, so the first one came from the packing lemma. The second one came from the covering lemma. So this is the case where I need both. Okay. So what have I finally showed is that any rate are less than is achievable. Okay. The next lecture will show that this is also tight. Okay, at the one-shot level. But yeah, so any rate less than this is achievable. So I mean, if you take the asymptotic IID, okay. So if you go, for example, look at in Elgamal Kim, so if you look at the asymptotic IID level, so the asymptotic IID level, this reduces to any rate. So of course it will be NR now because N cookies. And yeah, and then so well, so I'm just talking of the rate R per channel use. So we have shown in our second order analysis that the smooth mutual informations go to the Shannon mutual informations. So is achievable. Okay, so this might be familiar to you if you have seen it in a course, or this is the thing in Elgamal. Yeah, I'm here. Hello. Yeah. So we will stop here now. And yeah, but any questions before we wind up? Hari?
No, it's fine for now.
Sorry, I didn't get you.
Yeah, it's fine for now.
It's fine for now. Okay. Yeah.
Pranab, I just want to meet you after if you have a few minutes, is that okay? Like,
Okay. Let me do the following. I have a short meeting with another faculty member actually.
sure.
Yeah. Maybe around 2 o'clock or something.
Yeah, sure. Shall I send you a link?
Well, I think the best is to call on WhatsApp. I mean, if it's just one-to-one, then
Okay, sure.
yeah. Okay. I'll stop the record.
Yeah,